So in this video we're going to be looking at projectile motion again, and projectile motion can be analysed quantitatively by treating the horizontal and vertical components of the motion independently. And I'll show you what I mean by that in a minute. And basically you need to be able to do the following. You need to construct, identify and label displacement vector and acceleration vectors, use vector addition and subtraction to calculate net quantities, resolve velocity if it's given to you as a vector quantity into its vertical and horizontal components using the following two formula. I'll show you that in a minute. And basically you need to be able to determine the velocity at any point using trig calculations or a scale diagram, including using Pythagoras. So I'll unpack all of those dot points as we go. So the first thing you need to look at is, what is projectile motion? Basically, projectile is just basically any object that has either been thrown or dropped, launched, etc., that is being acted upon by a gravitational force. So throwing a ball up into the air, kicking a ball, etc., dropping a ball off a tower, blah blah blah, etc. Now, objects follow a parabolic path when they acted upon only by gravity. So for argument's sake here, a ball has been so a ball being kicked up into the air will be acted upon by gravity. So force due to gravity is acting directly downwards against the object, so it's slowing its path till it reaches its peak, and then as it starts falling back down to Earth, force due to gravity is accelerating it faster and faster back down to Earth, and it causes this parabolic motion. Again, this is what an object looks like if it's launched horizontally. So if it's chucked completely horizontally, it's still going to follow this sort of parabolic path. Now, we can break up this velocity up into two components: its horizontal component of velocity and its vertical component of velocity. Now, I'm going to show you how these equations work. You don't need to know, but I'm going to show you. But we can actually analyze motion, and we can figure out how long it will take to get to the top of its path, or how long it will take to get to the ground, or how far it's traveled, or what's its velocity at a specific after 2 seconds. We can do all sorts of calculations involving projectile motion. But first we need to break up its velocity into a vertical component and a horizontal component. So that horizontal component plus the vertical component. If you did vector addition last year, if we add vectors, we add them tip to tail. So this arrow here gets replaced here. So there plus that makes up this resultant velocity. But we can also break it into its components. So this is its vertical component and this is its horizontal component. And I'll show you, and basically if you get given its velocity and the angle that it's launched at, you can use its velocity and the angle it's launched at to find its vertical components and its horizontal components using these formulas. I'm going to show you some trigonometry, some right angle trigonometry, just to show you how it works. Now, hopefully we can remember with right angle trigonometry, I use the mnemonic SOHCAHTOA to help me remember the different trigonometric ratios. Now, basically, if this is our angle, this here is our opposite side, this is our hypotenuse side, and this down here is our adjacent side. So, the ratio, if we wanted to find this vertical component, so this component here is our vertical component. If we wanted to find our vertical component of velocity, we need to work out what ratio we're going to use. So this is our opposite side and this is our hypotenuse. So it's basically going to be sine theta equals our opposite side over our hypotenuse side. So sine of our angle is going to be equal to the opposite side, which in this case, this opposite side is our vertical component of velocity, over our hypotenuse, which is our original velocity given. And we can rearrange this. If we wanted to find our vertical component, we can multiply both sides by v, and we'll get that the vertical component is v, because we multiplied both sides by v, sine theta, which is what you'll get given on your formula sheet. So you don't need to memorize it or even be able to rearrange it, but I'm just showing you. you can go through the exact process to find the horizontal component, except this time it's our adjacent side and our hypotenuse side. So we can use cosine. So cos theta equals adjacent over hypotenuse, and therefore cos theta equals our adjacent side, which is our horizontal component, divided by our hypotenuse, which is our resultant velocity, and therefore we can rearrange this to get our horizontal component of velocity is equal to v cos theta. So we're going to quickly use these, but the main reason I'm doing this problem is to make sure our calculator is in degrees mode. So for all physics calculations, our trigonometry needs to be in degrees mode. So an arrow is shot at an angle of 55 degrees above the horizontal with a velocity of 12 meters per second. Determine the horizontal, so that's our velocity, resultant velocity, and then our horizontal component of velocity and our vertical component of velocity is what we need to find. So the vertical component is just v sine theta. Make sure your calculator is in degrees mode, so type in, so v is 12 times by sine of 55 degrees, and then to find our horizontal component, it's going to be v cos theta, and that's 12 times cos 55. And if we type them into our calculator, just to check that you've got it in degrees mode, if you can't remember how to change from radians to degrees, I can show you, but to put it into degrees mode, it's going to be 12 times sine 55, which gives me, to two significant figures, it's 9.8 meters per second. We don't need a direction because it is vertically, so it's 9.8 meters per second. Actually, we'll go up. So it's 9.8 meters per second. It is velocity, so it does have a direction. So it's 9.8 meters per second up. You wouldn't get marked down if you didn't. And then our horizontal component of velocity is going to be 12 times cos 55, which is 6.9 to two significant figures. So 6.9 meters per second to the right, assuming that the arrow was shot this way. Now, so that's pretty straightforward. You do also need to be able to calculate. So basically, we split it up. Okay, we got given the resultant, like the velocity of the object at some angle, and we converted it into its components, its horizontal and vertical components of velocity. But you also can be required to do the opposite. So if you find the horizontal component of velocity and the vertical component of velocity, which I'll show you later on, you need to be able to vectorially add them back together to find the resultant velocity. Now, we're going to do that here. So a ball that has been thrown at an angle to the right, so some ball was thrown at an angle, has contacted the ground, so it's hit the ground with a horizontal velocity, so VH is 18 meters per second, and it's going to be to the right, obviously, and so the horizontal velocity is to the right, and then it's going to be hitting the ground with a vertical velocity equal to 24 meters per second. Draw a scale vector diagram of this situation. Scale vector diagrams. So, for argument's sake, you could use your ruler and you could just make it 2.4 centimeters. So 1 centimeter could be, 24. So scale vector diagrams, you need a scale. So for argument's sake, you could have 1 centimeter equals 10 meters per second. So you could draw a scale diagram. So using your ruler is hard for me. The vertical component of velocity would be 2.4 centimeters if you use this scale. So you could use your ruler and draw a line. The way that we add vectors is we add them tip to tail. I'm not sure how much vector addition stuff you guys did. I generally actually like to start with the horizontal component first, and the horizontal component's 18 meters per second, so you might do it as 1.8 centimeters. So that's the horizontal component of velocity, and that's 18 meters per second to the right. And then the vertical component of velocity, we add them tip to tail. So that's 2.4 centimeters, which is, or 24 meters per second. Or meters per second. Sorry. Usually label it as VV and then 24 meters per second. You add vectors tip to tail. So draw a scale vector diagram of the situation. So you've done 1.8 centimeters and then 2.4 centimeters, and calculate the velocity. So with velocity, velocity has a magnitude and a direction. So here is the resultant velocity that the ball strikes the ground with. This along here is the resultant velocity. And it's doing it at an angle, so you need a magnitude and a direction. Usually we use, well, not usually, we do use an angle, and usually we use the angle between the horizontal and down to the direction in which the ball strikes the ground. So the angle there is the angle that we usually calculate. So to find a resultant velocity, we add our vectors, our horizontal and vertical components of velocity, tip to tail. And then we find this magnitude. Now, if you drew this perfectly to scale, so these would have been at a right angle here, so it's a right angle triangle, you would have, and if you measure that, you should get approximately 3 centimeters, which using our scale would be 30 meters per second. And then we'd need to calculate the angle using trigonometry. However, what sort of triangle is this? This is a right angle triangle. So we can use Pythagoras' theorem. And Pythagoras' theorem, remember, is just a squared plus b squared equals c squared. So basically, remember, this here, opposite right angle is always your c, and then your a and your b don't matter. Now, you don't have to, So to find our resultant velocity, which is our c, so our v squared is going to be equal to 18 squared plus 24 squared, and then to find v by itself, we'll do v equals the square root of 18 squared plus 24 squared. Now, pretty much always, we're using this to find the hypotenuse, so you can actually jump. Most students end up jumping straight to this line here, that this hypotenuse is equal to the square root of this side squared plus this side squared. And then they would write their velocity answer. So the square root, if you type into your calculator, I'll do it anyway, just to make sure. You guys can check as well. But that should give us, oops, I need a plus sign. That'll give us 30 exactly. So the velocity is 30 meters per second, but velocity needs a direction, so we need to find this angle in here. So to find this angle in here, we always use tan theta. So tan theta, because tan theta is the opposite side, which is, I'll do it in full. You don't need to write all these steps, but tan theta, so tan theta equals opposite, which in this case is the vertical component of velocity, which is 24, over the adjacent side, which is 18. And then to get theta, we need to do the inverse. So to get rid of tan, we actually take the inverse of tan, or tan to the minus 1 of 20, or tan to the minus 1 of 24 over 18. If you can't remember how to do that on your calculator, ask me. And this is why it's super vital that your calculator is in degrees mode. So tan to the minus 1 of 24 divided by 18. Opposite over adjacent. And that's 53.1. Or to two significant figures is just 53 degrees. Often, yeah, and 53 degrees below the horizontal. So resultant velocities need a magnitude, which we figured out was 30 meters per second, and the angle. often the textbook rewrites it out and says the resultant velocity was 30 meters per second at an angle of 53 degrees below the horizontal for completeness. But as long as you have the magnitude and the direction, in this case an angle, that will be fine. So you can be asked to do a vector addition of a displacement as well. Remember, a displacement is just the change in position of an object. So say if it might be object starts here and it might be what is the displacement of the object when it's reached the top of its path. So you might be chucked into the air and go like there, but it might say what's the displacement. So the displacement is going to be the change in position. So that's going to be the overall displacement. And so you're going to have a horizontal component of the displacement and a vertical component of the displacement, and then you can add them tip to tail. So later on we'll be able to work out how far something's traveled and how high something's traveled. So if it asks you to find the displacement, you're going to have to add the horizontal component of displacement and the vertical component of displacement vectorially, tip to tail, and then calculate the resulting displacement using Pythagoras' theorem. Yeah, you could also use a scale diagram, but I've recapped all that. So I'm going to stop that video here.